This playlist deals with some aspects of Eurocode 2 version 2023. Watch this channel for further selected topics. It's about clause 9, the serviceability limit state, and it's about minimum reinforcement for track width control part 5. In the previous video, we talked about the minimum reinforcement for track width control. We've seen the formula S1 that you have to use together with formula 9.2. And we talked about this coefficient KFL, which is H minus HC effective divided by H. In this video, we will talk about sigma S limit. And sigma S limit is given by formula S4, which is this one. And sigma S limit is the maximum stress permitted in the reinforcement to limit the given crack width we W lim calculate. The factor KW is 1.7, and it's converting the mean crack width into a calculated crack width. The coefficient K1 over R and K sigma 1 and K sigma 2 are different for bending and tension. It's in this table, written in this table. One remark, K sigma 2 in the code version 2023 of August 2023, the coefficient K sigma 2 for bending is indicated as 0.4 and for tension 0.3. Most likely this can be a typo, a typing error, because in the background documents we worked with a coefficient of 0.46 and 0.37. So it's a difference. But in this video, I will work with the values as indicated in the present version of Eurocode 2 2023. But bear in mind, maybe this will be changed in those two different coefficients. It also says that when you have to calculate sigma S limit for a situation where there is a bending and an axial force, then they say for intermediate cases, it will be conservative to use the values for pure tension. So that we've seen in the previous videos too, that in doubt for bending and axial forces, you can use the formula of pure tension and you are on the safe side. This is a graph on the x-axis is the limiting steel stress, and on the y-axis, it is the diameter of rebar that you are using. And there are different curves for different crack width openings. The blue one is 0.1 millimeters and the this color is 0.4 millimeters. So now you can easily estimate what is for each diameter you use, what is the allowable stress. This graph is constructed with a concrete cover of 25 millimeters, concrete quality of 30 megapascal. It is done for slabs, so it means that the diameter of the stirrups is 0, or it means that it's calculated for the steel which is in the most tensioned layer of the section. And this was done for a slab with a depth of 500 millimeters. Why did I choose those values? Because now I will be able to make a comparison with the similar graphs in Eurocode 2 part 3 of 2004. And we assume one layer of reinforcement. So it's the same graph as the previous one, but the dotted lines are the ones for Eurocode 2 part 3 on figure 7.103N. You can see immediately that there is a big difference. The blue lines are for 0.1 crack width, the red ones for 0.2, and the green ones for 0.3 crack width. Eurocode 2 part 3 did not mention graphs for crack width of 0.4 millimeters because that was not used. You see immediately that there is a big difference between those two values, and we can see that overall there is something like 25% less on sigma S limit. So the allowable stress in the steel, in the rebars, is 25% less for the same crack width. So we can wonder why. Why is this the case? What changed? Why can we not allow more stress in the steel to obtain a certain crack width? Now we will look into it a little bit more in detail. We look for beams, then concrete wall is C30, the stirrup diameter 10, concrete cover is 40. It's a beam of 800 by 400 millimeters. But to calculate minimum reinforcement with a crack width control, there you have too much parameters. You have the distance between the rebars, the diameters of the rebars. So you have too many, and the number of rebars, which is more or less the same as the distance between them. So you have too many parameters to calculate it. You have too many combinations. In principle, the smaller the diameter, the better for the crack width specification. And the more diameters you have, the better it also is for the crack width. So in principle, you should put as many diameters of 4 or 5 or 6 millimeters into the section, which is not practical, which is ridiculous. So now you have to make yourself, the engineer has to make some limitations. And for this exercise, I choose and from experience, I use the maximum spacing of the rebars for a beam. It should be smaller than 300 millimeters, and it should be bigger than 50 millimeters. In reality, the 50 millimeters is, for instance, the diameter plus 5 millimeters, or it should be related to the maximum size of the granulates of the concrete, and it must always be bigger than 20 millimeters. So if you take if you take a diameter of 32 millimeters, and then you add 5 millimeters to that, then you are more or less at 40 millimeters, and that's effectively the absolute minimum distance between the bars for a diameter of 32. Now, instead of making S also a function of the bar diameter, I've chosen to take an upper limit, and I take 50 millimeters, which is a realistic value. So the distance between two different bars must be bigger than 50 millimeters. And I also chose for diameter must be bigger or equal to 8 millimeters. So I'm not working with 6 or whatever. It must be bigger than 8 millimeters. For beams, in fact, I recommend 12 millimeters. But anyway, for this exercise, I've chosen diameter must be bigger than 8 millimeters. And n is the number of rebars. It's an integer, the number of rebars, and n must be always be bigger than 2, which is obvious. And the condition is that the calculated minimum reinforcement must be smaller than the provided minimum reinforcement, which is a function of n and phi. And now we have to make an iteration, because there is no direct calculation of IS-min possible. There is no one formula where you can calculate the minimum reinforcement, because everything depends on number of rebars and the size of the rebar. So you have to start just by experience. You start, for instance, with a diameter 10. I can also start with a diameter 8, but I know 8 will not fulfill the requirements. But in fact, you should start with diameter 8, because that was the smallest diameter that I envisaged. So start with diameter 10, then I guess n, and I can guess n because of this distance between the bars. And I have 4 times diameter 10, calculate IS-min, IS provided, which is 4 diameters 10, and you will see that IS-min over IS provided is bigger than 1, so it's not good. And that's the distance between. Then I add diameter 10, do the calculation again, and I see it will be now 1.11. So I'm in good direction. Now I take another diameter 10. I got 6 diameters 10, and I got 0.93. So this is the first combination of diameter 10 that fulfills both criteria. It fulfills this AS min and AS provided, and it fulfills S. So for diameter 10, I got one solution. But is this the best solution? We don't know. You don't know. So now we go for diameter 12. Do the same exercise. 3 diameters 12. The distance between the rebars is 144. I've got a unity check of 1.4, so I take 4 diameters 12. And I go on until the unity check is smaller than 1. So at 5 diameters 12, it's also a solution. Now I got 2 solutions already, 6 diameters 10 and 5 diameters 12. I can still go on and take diameter 14, diameter 16, diameter 20, and so on. Now you will see that for each diameter there is a solution. Of course, it's obvious. What we will do is we will take now the smallest amount of reinforcement. That's economic to work. So the best solution is 6 diameters 10. With 6 diameters 10 in a beam with a width of 400 millimeter width, that's quite crazy because the distance is only 60 millimeters. So in practice, in reality, we use 3 diameters 20. It's much practical, it's easier. But now you will see the difference, and it's 471 square millimeters, and this is 942. It's a huge difference. So now we make a lot of calculations, 12 iterations, just to find out that you can put anything you want, more or less. And each diameter has a solution. So this formula of calculating minimum reinforcement is very cumbersome. And it's difficult to program because you have 2 different parameters combined. You have the parameter n and phi, and everything depends on those 2 parameters. So you have a lot of solutions. We will now make the process a little bit more automatic. I've taken again a beam or beams. The concrete wall is 30 megapascal. The stirrup diameter is 10 and C is 30 millimeter, the concrete cover. And the depth of the beam is 400 up to 1000 millimeters, which is the most common sizes of beam depths. And the width, I always take it equal to h over 2, which is the optimum size of a beam. The distance of the reinforcement is between 50 and 300 millimeters. Again, this is my choice. Everyone can make a choice here. Huh? And the diameters, I will not use diameters smaller than 8 millimeters. N is the number of rebars, and I take it as an integer, and I make an automatic iteration on the diameter until AS min equals N times, until AS min equals the provided reinforcement. It means until unity check is 1. I cannot make an iteration on N. Why? Because N needs to be an integer to calculate AC effective. I cannot iterate on phi, on the diameter, because the diameter 2.3 does not exist, or 10.5 does not exist. So you cannot iterate on both of them. So, but I've chosen now because on N I need AC effective, and on phi, okay, it gives me an indication of what is the minimum or maximum size of diameter, I must say maximum size of diameter that I can use. So bear in mind, this is pure theoretically, and I've made an iteration on phi. So in every point that I calculated, it's not phi equals 12 or 10 millimeters or whatsoever. It can be 11.7 or something like that. In this graph on the x-axis, it is of course not FCK, but it's the depth of the beam. The depth of the beam, which is 400 up till 1000 millimeters. And on the y-axis, it is the comparison regarding the code 2004. By making those calculations, you will see that unity is reached at the dotted line, and you will see that in most cases, there is an increase in the required minimum reinforcement. You will also see that some strange things happen when you make a comparison with the present Eurocode of 2004, that for crack width of 0.3 millimeters or 0.2 millimeters, you have an opposite evolution when the concrete depth increases. That's not very logic. Why should that be the case? So if you have a crack width of 0.2, then it decreases with the depth of the beam. And when the concrete width is 0.3, increases. So it's not very logic. You should not, it's strange. On the other hand, once you reach 0.1 millimeter as a crack width limitation, then you have an increase in reinforcement from 1.5 to 1.8, which is a huge increase. Why is this? Well, this is because of sigma S limit, because of the sigma S limit, that there is a 25% decrease. The blue and the red line, we will investigate it further. We will give an explanation for that later. Now, the use of BC effective make the calculations always more complicated because they are depending on N and depending on phi. So when we put now BC effective equal to the width of the beam, then and you redo all the calculations, then you will see that the dotted lines is with BC effectives equals B. It simplifies the calculations enormously. So you see for the green, it makes no difference at all. The green, which is for a crack width of 0.1 millimeter, the full line is equal to the dotted line. So it makes no difference. So why should you use BC effective? Because it makes no difference. But for 0.3 millimeters, there is a difference. And that is the dotted line, but it's always on the safe side. It always gives you more reinforcement than if you calculate it with BC effective. Moreover, using BC effective makes the required minimum reinforcement less, which is also strange. You should expect it's the other way around. Like the blue line, you have a small increase for large beams, but the increase is almost negligible. It's always nothing. So there is no need to introduce BC effective. If you look at this for beams, you will see it's safe to work with BC effectives equals B. So I recommend just use BC effectives equal to B, and then it will save you a lot of time, calculation time. Now we will look at slabs. Maybe with slabs is different. We have FCK is 30 megapascal. The stirrup diameter is 0 because we are talking about the outermost layer of tensile reinforcement. Concrete cover is 30 millimeters. We take a slab with a depth of 250 millimeters. The width is 1000 millimeters. And for slabs, I've chosen the distance of the rebars must be bigger than 100 millimeters and smaller than 300 millimeters. For slabs, I've chosen a bigger minimum distance between the rebars. It's in practice, we do not use, or we prefer not to use more than 10 rebars per meter into a slab, because that's ugly to use more diameters per meter. And here also we take a minimum diameter of 8 millimeters. AS min must be smaller than AS provided. And in practice, there is no direct calculation of AS min possible. That's not possible. So we have to make it in iteration, but I've now deleted in between iterations, and I started with diameter 8 and I went to 10, 12, 14, and 16. And all iterations, for instance, for diameter 10, there were more than one iteration. They are different, and this is the best solution. Then you will see that if you look at it, that 5 diameters 8 is the best solution for a crack width of 0.2 millimeters. So it's the best solution. But all the other solutions, it's very strange, it's about 4 diameters. 4 diameters gives you also the best solution for different diameters. But this gives you the least reinforcement, minimum reinforcement. Taking now the crack width limitation equals to 0.1 millimeter, then we see immediately that you need 9 diameters 14 to have a unity check of 1. So there is a huge difference when you specify minimum reinforcement with a crack width of 0.2 millimeters or 0.1 millimeters, your minimum reinforcement increases by a factor 5 or 6. So be very careful to define a minimum required crack width opening. We can now, the previous calculations were with N and phi integers. Now we can make it a little bit more automatic. And again, we will go for an iteration on phi for n an integer. And for n, it goes from 4 up to 10. This has to do with the spacing of the bars and that we have limited, that we have chosen ourselves. So now n, you can inverse it, and n is 4 up to 10. When we do that, and we iterate on phi, and then from all iterations, we take the minimum reinforcement, the minimum amount, then you will see this graph. On the x-axis, it's the crack width, and on the y-axis is the minimum reinforcement. And you see a strange thing, something almost linear, and then something horizontal. The horizontal, that's where the minimum reinforcement calculated by formula 9.2, that is without crack width limit and with sigma s equal to fyk, that is when this is dominant. You remember that the minimum reinforcement must always be bigger than the ones in calculating formula 9.2. And that's why you have a straight line here. And then it goes up. This means that the formula of annex S, that the crack width, the specified crack width is important for the total amount of minimum reinforcement. Now, in most cases, when you see all those calculated cases, in most cases, IS min is minimum for n equals 4. In most cases, not all of them, but in most cases. So this is also something to remember. For n is 4, the required minimum reinforcement is the best. And this is because the BC effective is different from B. So when BC effective is smaller than B, is smaller than 1 meter, and that because we are working with slabs here, then N is 4. If BC effective is bigger than B, so BC effective is replaced by B, then you do not reach a minimum. So this is also, again, strange, so like the same thing that we found with beams, that BC effective makes the needed reinforcement lower, not bigger, lower, which is strange. Furthermore, what is quite disturbing is that why is the minimum required reinforcement without crack width specification, why is it dominant when the crack width specification is 0.2 and 0.25 millimeters? This is not logic, because you should expect that as from 0.3 millimeters, then or 0.4 even, add some 0.3 millimeters, then if you specify a crack width, then it should kick in that you need more reinforcement. But it's not the case. So you can use the 9.2 formula without using sigma S limit and things like that, up till a crack width limitation of 0.2. It's not logic. And then once the crack width specified crack width limitation is dominant, once this is happening, then it's almost linear. The minimum reinforcement is linear with the required crack width opening. This is also not something that one should expect. It's something my experience tells me there's something wrong here. It cannot be linear. For flaps, we will now look at different slab depths going from 150 up to 500 millimeters. B is 1000 millimeters. Again, the distance between the rebars is between 100 and 300 millimeters, and the maximum and the rebar must be at least 8 millimeters. We take n as an integer and we make iterations on the diameter. And we do that until the unity check is 1. We've done that on this graph. You see, again, this is not FCK, but it is the depth of the slab, the total depth of the slab, going from 150 to 500. And this is the ratio with the value of Eurocode of 2004 as reference. And again, we've done that for a crack width of 0.3 and 0.2 millimeters, which is red and blue, and 0.1 millimeter, which is green. Above the dotted line, it's an increase in minimum reinforcement, and below, it's a decrease in minimum reinforcement. Here again, you will see that for crack width limitations of 0.3 and 0.2, you have a decrease in needed reinforcement. So remember that for those two crack widths, AS minimum, so the minimum reinforcement was determined by the formula 9.2. And this is why, because at the red curve and the blue curve, the BC effective is dominant and reduces the needed reinforcement, minimum reinforcement. You have an increase for a crack width limitation of 0.1, and it's a very significant increase up to 1.7 times what we used to today. Here we can also now see what will happen if we choose always BC effective equals to B, which is the dotted lines. And you will see that for a crack width of 0.1 millimeters, that the dotted line is above, or it's in fact the same as with BC effective, only for very small slabs with less depth as 250 millimeters, you will have an increase. But this is completely nonsense, in fact, because the value of 0.6 is where BC effective is smaller than B, and the value of 1.4 is where BC effective is equal to B. And there's a big difference. So why should you need less reinforcement if you use BC effective? It's mind-boggling. You also see that for crack width of 0.2 and 0.3 millimeters, if you use BC equal to BC effective, you have a nice horizontal line around unity. This you can wonder why are we using BC effective now? Because the use of BC effective decreases the minimum needed reinforcement, and if you use BC effective equal to B, it's safe and easy to implement. because you can see that those two dotted lines is around the same value as we obtained from the Eurocode 2000 in 2004. So what changed in the world? Because we should now need half of the reinforcement, which is very strange. So I recommend to use in all formulas BC effective equal to B. It gives you more logic results.